Hello, everyone. I'm going to talk about one systematic today. This is a systematic that affects calibration. It is small sky model areas degrading calibration, and I'm just going to give kind of an overview of what different folks in the collaboration are doing to solve this problem, myself included. So what does it mean to degrade calibration? We have calibration solutions that have errors. That doesn't surprise anyone. But more importantly, these calibration errors are frequency dependent, and that's what we're really worried about. Because the whole idea behind detecting the EoR is that we can separate the EoR from foregrounds because foregrounds are spectrally smooth. As soon as you have any kind of frequency dependent calibration errors, those errors get applied to data and they turn the spectrally smooth foregrounds into something that's frequency structure that's going to completely blow out the EoR window, and you don't get to see an EoR signal. So this is why this is a big systematic for EoR science. So how do these sky model errors degrade calibration? They do this generally through faint missing sources in the calibration catalog, and this is because the instrument PSS is frequency dependent. This shouldn't be super surprising to anyone, but this is a simulation of a single point source through the MWA as a function of frequency, and you can see that PSS is moving all of these little source side lobes around. So it's also important to note that this is very instrument dependent. Different instruments have different PSS. So the amplitude of these side lobe bits is going to give you how important this effect is and how much it degrades calibration. Missing sources in the model introduce frequency dependent errors, and this is why this is frequency dependent event. So this has been identified a few times, but one of the papers that identified this was Nicole's 2016 paper, where she simulated calibration to a perfect model and created a 3D power spectrum here. And then simulated the same visibilities, but now calibrated with missing sources. So the important thing to note here is comparing these two, you have more power in this EoR window when you have missing sources in your calibration catalog. So that's exactly the problem we're looking for. And then a more straightforward mechanism of error is that we simply can't calibrate where we don't have a model. So this is going to become important later in this talk. We can't calibrate to short baselines if we don't have a diffuse model. We generally only calibrate for point sources, and this means that we simply don't calibrate to short baselines to any long baselines. Okay, so now I'm going to talk about different ways to resolve these problems, to mitigate these errors. First, I'm going to talk about redundant calibration and show that it is not an effective way of mitigating this error. And this is similar to talks I've given before, including at the last project meeting. So it might be a review for some of you, but I talked about it again. So this is redundant calibration. The idea behind redundant calibration is we have these highly regular arrays. We have a lot of the same baselines. We impose a prior that redundant baselines are seeing the same signal from the sky, and we use that to calibrate. So sort of naively, you would say, awesome, we're calibrating out a sky model. We shouldn't have these issues based on these tiny errors in the sky model, but it turns out we do. And the reason we still encounter these errors is that redundant calibration consists of two parts. So this is the framework that we developed in this paper that was published recently, where we talk about redundant calibration being composed of relative calibration and absolute calibration. So, relative calibration is the sort of redundant part of redundant calibration, where we match these visibilities from baselines. It does not depend on a sky model, and the important part for this is that it's degenerate. And it's degenerate in a few parameters, and these parameters are per frequency. So then we have absolute calibration, which is the step where we actually fit these degenerate parameters. And what I want to emphasize is that redundant calibration really fundamentally consists of these two parts. You don't have physically meaningful calibration solutions without both relative and absolute calibration. This sort of begs the question, we have these really horrible sky model errors that appear in sort of traditional sky-based calibration. What does it mean for redundant calibration. So we went ahead and simulated this with a nice redundant hexagonal array that looks like this. Kind of repeated the work that was in Byrne et al. 2016. We came up with these simulations where we have perfect calibration on the left, and calibration to an incomplete sky model on the right, where here we're only allowing errors in absolute calibration. We have perfect relative calibration, which you can imagine, meaning that you don't have any non-redundancies in your array. This is also noise-free. And we have significantly more power in the EoR window with these absolute calibration errors. And then we can also quantify this effect in 1D. So this is just the colored lines here are plotting the excess power in the EoR window. The blue line here is from the array I just showed you, the hexagonal array. The red line is from a hexagonal array that's more of like a Hera-style array where there's 3 parts that are offset from each other. And then this orangey-yellow line here is an array where we've randomized the antennas but still constrain them to have the same radial antenna distribution. So what we actually see here is that good baseline coverage mitigates this error, and this is going back to that instrument PSS, where if we have larger sort of side lobes, we end up getting higher temperatures of the air. And another interesting thing to note is that this dotted line here is that same randomized array with just per antenna calibration without any kind of redundancy stuff applied, so more traditional sky-based calibration there. And it's still doing better in these simulations than the redundant arrays that only have absolute calibration. So that's kind of why redundant calibration can't save us on its own. So what now? The problem is that we need to eliminate false frequency structure in our calibration solution. And this is a really critical aspect for detecting EoR. So one way we could do this is we could average our calibration solutions across frequency. This is, a pretty straightforward, naive approach. We don't want extra frequency structure. We can get rid of all frequency structure. And this actually doesn't work because a major emphasis of calibration that we need to do is to fit the true frequency structure of the instrument. So we will also contaminate the EoR window if we're not fitting that structure. So let's not do that. Instead, let's reduce our calibration degrees of freedom across frequencies while still preserving that structure. So this is really what we need to be doing. Also, Wenying talked about this a lot, and Nicole's also used this. So their 2 limit papers use autocorrelations to calibrate the bandpass. And I stole this plot from Nicole's thesis. Thank you very much. So this is showing the bandpass of the MWA using cross visibilities and autos. And what you can see is that the autocorrelations are a lot cleaner. There's less high modes in the bandpass structure. You can see a cable ripple as well as the coarse band structure. So that's a really promising area, and both Wenying and Nicole have had a lot of success with that. And then we can calibrate to short baselines only, and this is really what I'm working on to mitigate this problem. And the reason this works is because missing sources in the calibration model produce a maximum error mode that relates to the maximum baseline length. So you can imagine you have this missing source in the model. It has side lobe structure that's moving around as a function of frequency. You're going to get your maximum error mode from a very long baseline and a missing source at the horizon. So if you restrict your baseline length, you can restrict your errors to low mode. And basically, this is what we found in simulation, that we have a contaminated region of the power spectrum space and then a safe zone that's proportional to the maximum baseline length we use in calibration. So this really makes the case for short baseline calibration that we need to be using these. And like I said before, we can't calibrate on modes where we don't have a model. So we need a better diffuse foreground model. This also goes back to polarization, as we were just talking about. We find that diffuse emission is extremely polarized, and so we need to get polarization right to do that. So this is my job. This is what I'm working on. A polarized diffuse foreground model. Stay tuned. I feel like I've been saying this a lot. Some of you are probably getting tired of hearing this. I was thinking about presenting preliminary results, but I also don't think it makes an interesting talk to talk about all the bugs I've fixed recently. So I'm not showing you preliminary results, but I am promising a diffuse foreground model coming soon and the improved calibration that comes from going to shorter baselines. So in conclusion, frequency-dependent calibration errors are a limiting systematic for EoR science. These errors come from faint foreground model errors, and we have these promising error mitigation techniques that include restricting our degrees of freedom across frequency, using the autocorrelations, and doing this for baseline calibration. And I will finish with that and do questions.
So, LOFAR is the polarized maps. Some of the, I think it was near the end here, I can't remember exactly what. There was diffuse polarized stuff that was long in one direction, so short baseline, but sharp, like in the polarized sense, like filamentary, almost like a stained glass window it looks like, right? Sharp edges. So to characterize that well, you would need a short baseline and a long baseline to resolve that structure. How can I think about dealing with that?
That's a really good question. So we're doing this polarized imaging with the full MWA. And then, so hopefully we would do stuff like that. Then when we go to calibrate, we want to limit it to short baselines, but that has nothing to do with the modes that have gone into the model. We have played around with limiting what baselines go into the model, and that's something we can still think about. But there's nothing inherent to the model that it has to be made with only short baselines. But, yeah.
I'll just add, remember what LOFAR considers a large angular field?
Yeah.
MWA. I'm trying to pull up yellow images. But I think north-south of a degree or two is the long size. And still not an MWA field. A really old-fashioned method of looking at redundant calibration is using UV crossing points. Well, as your one baseline maps to a particular UV cell and a different baseline of a different length and orientation at some other point maps onto exactly the same UV cell. So it's like non-simultaneous redundancy. Yeah. So you have the same baseline looking at the same sky at different times.
Yeah.
And with as many antennas as you have in the MWA, you get thousands and thousands and thousands of UV crossing points. So has anyone ever thought about using this for the MWA as a constraint on calibration? It's what we used to do 25 years ago for the LBI.
Yeah, but you have dishes.
Yeah, I know. Yeah.
That's right.
So
but those you don't have track.
Sorry, Adam. Well, the beam is moving, so
The beam shape.
and if you try to track, your shape is still moving, so it's not redundant at precision.
And actually, this is a proposed, try to take care of the frequency axis in redundant arrays. You say, okay, look, we can get frequency structure by saying when does this redundant baseline line work with that other redundant baseline at different frequencies, and it's the same problem. The beam changes so much in the function of frequency, it doesn't work very well. It doesn't work at the precision that we need.
And my understanding about that is that some of you have more redundant baselines, but I've never actually thought about that, so correct me if I'm wrong, but that one actually breaks your dependency. You still have an overall amplitude and phase.
Still need absolute.
Right.
it doesn't solve the second
Right. So it might be able to constrain relative calibration. What I'm arguing here, which definitely is the whole story for redundant calibration, but what I'm arguing here is that even with perfect relative calibration, your absolute calibration really limits you with this type of systematic error.
I thought there was a piece for it. It's one of the comments on the low part part, the part that is. Some of that really appears when you break up into different variable depth ranges. Which is extra complicated because then it composes the structure and frequency events, which I wouldn't be able to. Yeah, so that's not exactly.
That's the thing that gives me anxiety is thinking about it.
But so just to point that out, but the question was just about the model that you're developing for the polarization. Is that all sides? Do you cover the side lobes as well, or is it just sort of focused in the main lobe?
Yes, it is covering the side lobes. It's about half of the photometric. So it's a large region.
It's the guy that's up on EoR 0 is when we're looking at EoR 0.
Yes,
Is that still the one that was done with a bunch of
Yes.
different problems?
Yes, over EoR.
You just stated it.
Oh.
It's a set of 2015 data. Mosaic.